first of all, I just a couple of things about this lecture here. As you can see in this slides, there's quite a number of slides, 47 pages, about 46 of them. As a caveat, this lecture is pretty long, but I will try to distill it as much as I can. So just a high-level sort of understanding on how this OOP works, but also what OOP is really about, because you probably have heard a lot about object-oriented programming. So this is what this lecture is. Let's kind of delve right into it. Before we get into objects, you probably have seen this, and from a couple of slides ago, I was going through these data structures. So these data structures are kind of abstractions, storage units that you can think of these structures as something that, or even an object that has specific sort of property associated with it. And these properties are embedded in various different methods, right, that you can call on, or maybe a property is associated with the objects themselves, like lists, like dictionaries, like tuples. Every single one of these data structures or types have their own properties, specific behaviors that you can invoke on. So these data structures are what we call objects too, okay? List is one of those objects. List has a slew of methods associated with it. So these methods are invoked using a dot, right? So you have dot append, dot extend, dot insert, dot remove, dot pop. And these are methods. This is what we call application programming interfaces, APIs. So objects at runtime can effectuate, right, different behaviors based on which methods that you call on to do so. And they occupy memory spaces, and they carry specific behaviors. So these are what we call data structure at runtime, and these are objects, okay? Let's move on. So this is the API. API is, what is this? Okay, SQLite 3. This is a embedded in-memory databases that are available that could be invoked via Python. So you can use the SQLite 3 library modules to basically come up with your own in-memory databases at runtime to store data. And the reason why I'm showing this, or I guess the reason why we're showing this in chapter 14 is to illustrate that this database, even when you import it through the import modules in Python, it's also itself an object. But SQLite 3 comes with a whole bunch of stuff, like even the connections, or the method itself that allows you to connect to that database of interest itself is a connection, is an object. So this is what we call a class. At runtime, it becomes an object, okay? So as you can see from this slide and this slide, there's a whole bunch of objects we're talking about. So what exactly is an object? Before we get into what an object is, let's talk about what is a program, right? And then we can take it from it. This is precisely the reason why you see this slides right here. Okay, so without further delay here, let me make sure I get my annotation tool up and running. Okay, so process, okay, and then you have input, you have output. So this process is akin to methods or functions that we had all throughout this whole semester. We've been doing this, right? It is a black box. It takes a certain amount of input and you can get an output out of it. So one example is this. You can have this input from the user, and once you get the input, you can convert it into an integer and calculate what the increment of that input is, and then try to print it in the outputs. So this output is your computer screen, okay? You're printing it. So it's going to your console application, and the input is coming from the user, right? So this is user, and this is console applications, console display screens, okay? So what we were just talking about object. What does that have to do with the process? So what is a process? So process is more than just your CPUs, okay? Process is also, well, in computing terms, a process is a collection of, it's not a collection, it's a, at runtime, it's a, it's an operating unit that allows you to execute programs at runtime. So runtime is whenever you press the run, or at runtime is whenever you just restarted your computer and now you're loading your operating system. So that's what we call runtime. So this process allows you to transform or modify your input signals, giving you specific outputs to it. So what does that have to do with the object? Then again, you can think of these processes, right? So typically in a computing unit, we have multiple processes. Each processes has their own, each process at runtime has their own pool of thread. Okay, so you can think of it. Let me just annotate this to illustrate, because we're not in front of a blackboard. So let me do this. So at runtime, you have these processes talking to each other. Okay, and it's very possible that if you have Windows at runtime, you may have like 10 different processes running. So one process will be running your operating system called Windows. Another process would be responsible for communicating to your mouse, right? Your external keyboard devices and stuff like that. So I'm using these blue circles to represent processes. So there's process 1, there's process 2, process 3. Usually each process has a PID associated with it, process ID. So we're just gonna make it really simple to notate them with a number. These processes talk to each other through what's called inter-process communications. Inter-process communications happens in many ways. Sometimes they use communication queue or some sort of messaging bus that relays the message back and forth. And the reason why this happens is because inside each process, you also have what's called a pool of thread or thread pools. So a thread, T-H-R-I, let me just write this down. Okay, a thread is like, a thread that goes, that you use to sew up your clothes or something like that. So the same thing, right? Threads. Each thread is an operating unit that is responsible for completing each task of sorts. So you can have multiple threads. These threads sitting inside this unit does not know the existence of threads sitting in a different process unit, okay? Because threads sitting inside each process has its own memory space, right? So they don't share with threads from the other processing units. But anyway, long story short, you can treat these processes as like its own object. So the way that is drawn here shows that you have multiple processes or multiple threads that can talk to each other. And you don't necessarily need to know, and you don't typically know what is inside each thread, okay? You don't, and you shouldn't care about it either. And this is the beauty of object-oriented programming, because you can trust, okay, each object at runtime to know what it's doing, right? You can trust that it knows what it needs to do. So that's what this analogy is, okay? So let me just kind of switch slide, because before it gets too abstract, let me move forward to the other one, the very next slides. So object-oriented. So what does that mean? Well, you have a lot of objects out there, and you're gravitating towards basically entire code. It consists of a whole bunch of objects. Then that code is what we call object-oriented program, okay? And object-oriented programming is that practice, that general paradigm, a design, or set of methodologies that allows you to get to that coding style. Python is OOP, okay? It's an object-oriented program. C++, Java, JavaScript, Ruby on Rails, There's a lot of programs out there. They are all OOP based. Okay, you don't see a lot of non-object oriented programs anymore. So what is the opposite of object oriented programs? Meaning, you know, when I say object oriented program, it's a whole bunch of objects that can talk to each other. Okay, and not only that. Okay, what is that illustrated in the previous slide is the fact that object can also inherit from each other. Okay, an object also has the ability to encapsulate data, meaning I can make certain data public, I can make certain data private, which means only it itself can see it, but other people won't be able to see it. I can also make data available to everybody who inherit me, right? So there's a lot of stuff that you know, happens in the object-oriented world. C++ started the it's basically the father or the mother of object-oriented programming, because C++ took off from C, and C is what we call procedurals. So on the one hand, you have procedural language, which means a function talks to another function, which talks to another function, which talks. On the other hand, you have this more advanced thinking, a paradigm called object-oriented. So object-oriented programming took off from procedural languages, and that started the entire shift, this newfound thinking, right? That basically, you know, was the basis of Windows back in the 80s. So as you know, Microsoft started, you know, utilizing and start making OOP popular with their Windows 3.0, right? Software operating system, and so did Apple, right? And then Java came around. This is all just history, okay? And Java came around, you know, back in 1994, 93-ish, leveraging object-oriented programming paradigm from C++ and taking it to the next step. And then, of course, you know, JavaScript came around, the web language technologies evolved. You start seeing a lot of these OOP languages floating around. And then people then talk about what's called objective, right? Not objective, functional language. So functional programming languages are also evolving from OOP as well. So Scala, Haskell, these are all OOP, right, on the very bottom, but they make it functional. So there's a lot of that, the programming evolutions that came out of object-oriented programming. But for the purpose of this discussion, we're talking about the fundamental, the most fundamental object-oriented stuff, okay? So with that said, let's talk about what, kind of go through what author is saying here. A program made out of many cooperating objects. So this is exactly what I just illustrated here, right? This entire block right there. Instead of being the whole program, each object is a little island. You can just treat each object as its own unit kind of thing, right? It's got its own brain and power to do what it needs to do. So that's what the logic is within the program, and cooperatively, meaning they can work with each other. A program is made up of one or more objects working together. Objects make use of each other's capabilities, okay? So with that in mind, you can think of your list, okay, at runtime, your tuple at runtime, your dictionary at runtime, or even a string, right, instance that you have at runtime. Every single one of these is an object. And so now I just enlisted 4 different types of objects at runtime. And of course, at runtime, you can have a 2-dimensional list. You can have 1-dimensional list. You can have various different objects of the same type. You see what I'm saying? Same type floating around. So it is very possible that you can have hundreds of objects at runtime working collaboratively, right, or cooperatively to achieve something. And you as a developer, your job is to make sure that these objects are instantiated, meaning created at the right time, at the right spot, and they're made use efficiently, right? Make use of each other. So what is the purpose of an object? The purpose of the object is to encapsulate their own brain, right? So basically what you're doing is you're creating a robot or human beings, right? You can think of it that way, but objects is different than human beings. But you get the idea. That each entity, right, object, has its own brain, its own logic to accomplish things, right? So this object being a list has a whole bunch of methods, right? You can do dot append, you can do dot clear, you can do dot index. There's a lot of methods you can invoke on. So typically what we're talking about when we're talking about objects, right? Let's say this object's here. Object has two things embedded in it. One is a collection of properties, right? So these properties could be, let's say if this is a automobile object. So these properties could be the color of the mobile automobile or the vehicle, how many wheels this vehicle has, what is the, this car have, windshield wipers, right? This is a Boolean. At the same time, in addition to these properties, right, you also have what's called methods, right? So I'm just going to draw individual circles here to indicate the methods. So one of these methods could be run, right, or start the engine. The second method could be stop, right? So you can make this car run. You can also make this car stop. This is what we call behaviors. So as you can see, an object can have a collection of properties associated with it that describe what this object is at any given moment in time. It could also have a collection of behaviors that you can dictate this object to do, right? So by invoking is kind of like sending a message to it. So I'll get into that later on. But just to be, a super high level here, an object can be operated upon or could be executed or invoked a specific behavior on top of it. So a behavior like start the car and stop the car, or maybe pause the car. Well, there's no pause. You can make it, what do you say? You can make it run faster or speed up, right? Maybe there's another method that's called speed up, right? And you can set the speed settings of the car once in motion and things like that. Okay, so that aside, I just wanted to make sure everyone gets it. When I say object, these are in the most general sense of the terms. Anything you see in a programming world, it starts with a class. Okay, class becomes an object. Okay, so this is a class, and it becomes an object at runtime. Okay, so this class that has properties and behavior that you saw. One example is the stuff that we just saw here. Okay, so this is a class, right? A data structure. This is the list. This is a class. So at runtime, they become objects. Okay, all right. I think we spent way too much on this part. Let me just get to any questions about this so far? Okay. Let's talk about this objects here. Okay, so this is just one object. So object is a bit of a self-contained code and data. So we talked about that, right? The self-contained means it's got its own properties, right, and behaviors. So a key aspect of an object approach, right, is to break the problem into smaller, understandable parts, divide and conquer. Okay, this is one example. If I want you today to build a zoo, okay, zoo software, or maybe not zoo, forget about that. Let's just talk about, I want you to build an ATM machine, okay? This ATM machine is in code, Python. Now, this ATM machine is pretty big, right? What does ATM machine have? ATM machine has keyboards, right, on the outside. It's got camera features. It's got some internal logics. It also has connectivity to some databases, right? Some storage that stores, I don't know, maybe 50,000 users, bank accounts. And what about those bank accounts? Those could be savings account. They can be checkings account. They can be my retirement account. So using an ATM machine allows a user to fetch a specific set of the account that user belongs to, right? It also allows the user to log into, right? Before getting into your account, you have to key in some passcodes, right? And said, I want to hit it, and then you log in and blah, blah, blah. It also has a card reader, because without a card reader, how do you log into your ATM machine account, to account through an ATM machine, right? So it is reasonable, right, to assume that if you're building an ATM machine, that machine has to be broken down into understandable parts, right? And those parts are what I just described. Okay, we're not designing an ATM machine here, okay? So don't worry about that. But you get the idea. Objects have boundaries that allows us to ignore unneeded details. So what does that mean? Well, objects do not merge with another object, okay? So you don't see these two objects kind of merge together with something in between, right? So objects are typically stand alone, right? So means, what does that mean? List has nothing to do with tuples. Tuple has nothing to do with dictionaries, right? These are two different objects that you can have at runtime. There is a certain boundaries between them, meaning there is no shared code, okay? Now, we've been using objects alone, so like this is like just what I described, right? Dictionary, integers, strings, float, Boolean, right? Things like that. So these are all objects, okay? So with that in mind, just remember the key aspect of object, right? It's the fact that you can break a complex problem into many different objects around time, and each object, technically or theoretically, should not be should not overlapping each other, because then you would be creating what we call dependencies in code, which is not good. It makes the code a lot less desirable, a lot harder to maintain in the future. Okay, so let me clear this drawing and move on to the very next one. Okay, so so great. So we see a cloud here with multiple objects. So these objects can interact with each other. Dictionary itself could be an object, whatever these objects are. And it's simply just making use of these string objects and dictionary objects as a way of storing or fetching data to and from. And of course, you're going to have the input and output coming out of it. So at runtime, so I would say at runtime, your runtime environment is represented by this cloud. Okay, this entire cloud is your runtime environment. Okay, in actuality, this is a lot more complicated, right? Like I said, you can have hundreds or even thousands of objects interacting with each other at runtime. Okay, cool. One example is your part 3. Your part 3 game of life. I would say easily you could have had probably 50 objects, floating in space at any given moment in time. Okay, so your project is not as complicated, but you get the idea. Having these objects interacting with one another at runtime. Okay. Here's another one. So what is the difference between this and this? So now you were talking about object, and then you're talking about string and then dictionary. In reality, what you have is simply just code and data. The reason why there's code and data is because, what does code mean? Well, code is static, right? Static. What about data? Well, data could be static or dynamic. Okay. So the code itself is basically the kind of the framework that serves the data. Okay, so what gets exchanged between these objects is really not the code themselves, even though sometimes they do spit out code from one to the other, but that's what we consider as the data. Okay, so let's just for the sake of simplicity and brevity, let's talk about data. So really what gets exchanged is the data. So this could be read-only data, or it could be the fact that one object wants to write this data to the other side. So you have these exchange of data through these what we call objects. An object is a whole bunch of code plus data in it, nothing else, right? So these code, if you don't run them at runtime, they're what we call class, right? Which is a blueprint and its analogy. When you create an object, similarly, that object at runtime is the 3-dimensional house that you create based off of its blueprints, right? So blueprint, 3-dimensional object, house, class, object. Okay, so this is the analogy that we're trying to do to get at. One is static, one is dynamic. One is static, when it's at runtime. Okay, dynamic is the same as runtime. Okay, that gets decided when you hit that run button. Okay, so that's what I wanted to say about this part. Any questions about this? Page 10. Okay, well, it's 7:52, so I'm gonna go on for maybe now 10 more minutes, and then we take a break. So this object hides details, so allowed to ignore the details of the rest of the program. That's exactly it. So whatever is in the code here may not be relevant to the code sitting outside of it. What does that mean? Well, it is very possible that this code here is private to this particular object that I have here, okay? And that code has no bearing to what these other codes are, okay? These are all different. And they could also be hiding these code from each other, meaning this is what we call object encapsulations or data encapsulations, excuse me. Data encapsulation. What does that mean? Data encapsulation means data hiding, right? What information, whatever information you have sitting here in this object stays here. It's kind of like what happens in Vegas stays in Vegas. Same thing here. This is Vegas, is this object. And whatever happens inside of it stays inside of it. This is pretty much your OOP principle number 1, which is data encapsulations. The ability to hide data. This is a security feature that you see in OOP that you do not see in other non-OOP languages, like in C. You can't really hide these things. But in C++ or in Java, you can hide your data. Okay, so the object hides detail that way by encapsulating their details to allow other people from seeing it. Okay, so this allows you to create that boundary I was talking about to make sure that this object, has everything that it needs, but nothing more, right? Okay, so any questions about that? Let me clear and then move on to the very next slide. Okay, object hides data without the rest of the program to ignore the details about us, right? So this is kind of the similarity that we had before with one object. Now you have 3 of them, right? In this case, the 3 objects kind of talk to each other, but they kind of they don't know the existence of this 4th object, which is kind of hidden because the entire 4th object now is it's really not hidden. It's just not. They're not accessible. Okay, so this one is not accessible by the rest of the world, and you can totally do that by either having a singleton with some data encapsulations as part of it. Like you can set it's meant to be private, so nobody else really has access to it, making it completely independent from each other. And this is a power of OOP as well. And of course, you can accomplish the same through what we call inheritance or polymorphisms, but these are more advanced topics that I will develop later. So yeah, I mean, I mentioned this maybe a couple of weeks ago. A template is kind of like your construction blueprint is what we call a class, okay, in computer science. So a class is what I just illustrated in page 2 or 3, where you see the API. Those are class, okay? Class definition, class declarations, and also the application programming interfaces, which is documentations. In this case, class is a template, and class also has what we call methods, right? At runtime, your the methods inside of the class becomes the object methods. We don't really use message a lot. The message is a pretty old term, and you see them in Ruby on Rails too. In order to invoke this methods, how do you invoke it? You have to tell, right, the object, hey, I want to use that one. I want to use that. So it's like sending a message, right? So without sending a message, how do you let, or like without communicating with the object through this message, how do you let that object know that, hey, I want to invoke you. I want to ask you to stop, right? So they use this term called message to signify methods. So, but you guys know what a method is, right? You've done quite a number of methods already in your code. So you should know what that is. You also know what a field or attribute is, right? So one example is your game of life, right? Part 3 or part 2 even has maximum number of columns, maximum number of rows, right? These are predefined, right? 30, 60, whatever that is. These are fields or attributes. In my other slide earlier, I was talking about properties and behaviors. So in some textbooks, you see properties and behaviors. They're akin to fields or attributes. So fields or attributes are properties. Methods or message, these are what we call behaviors, right? So thinking abstractly, right? The entire object has these properties or inclinations to do something. It also has certain set of behaviors, right? So method, fields, right? Message, field, or method, attributes, or properties and behaviors, right? So I'm using these terms interchangeably to make it a lot more kind of suitable for learning. And because hey, you never know, two days later, next year, you come across a textbook and they start talking about properties and behaviors. What are they? They are methods and fields. And some textbooks use method or attributes. Okay, so yeah, you see a lot of these things that are kind of floating around. In database terminology, they use fields and attributes as well to indicate a particular column inside a table. But anyway, that is kind of beyond the scope of our discussions here. Okay, I want you to remember though, at runtime, okay, this is all static, right? Let me just get rid of this. This is what happens when you use your mouse to to draw things, and there's so many different things going on at the same time. Okay, so these three, okay, is static, okay? And I am so sorry about the drawing here. This is a static step. And what is dynamic is what we call object, okay? So I want you to remember this when we're talking about, oh, sorry. Let me navigate back. When we're talking about object here, object is dynamic, whereas class, method, fields, these are static. So static means sees what you, I don't know. What is that term there that says that what you see is what you get? Okay, so what you see is what you get on your in front of you in this Python code is static. It's a class, it's a method, it's a field. But when you compiled and run your code at runtime, where Python runtime interprets your compiled Python code, whatever is interpreted, it becomes a whole bunch of objects at runtime. Okay, so when we're talking about objects and instances, this is these things has memory in them. Okay, at runtime. So one of them is static and the other one is runtime. Right? Static means non-compiled, non-runtime. Runtime means basically in real time, and the entire class has been instantiated. Instantiated meaning created, right? Meaning there's memory associated with it. Okay, so instance, object, they're pretty much the same thing. Okay, there's a lot of yeah, I know when you're just learning this for the very first time, you probably get confused with the terminologies, but it is my job to keep reusing these terminologies over and over again, and I hope I get a chance to do this a lot more so that you get it, okay? But anyway, so that is the difference between class and object, and from definition standpoint. Do you guys have any questions about this? Okay, it's 8 o'clock, so I think I can probably just go through a couple more pages and then we'll take a break. All right, let's get going to the next one, which is this one. Okay, terminology class. So a class is it's an abstract container. It's a invisible boundary that groups certain number of things. So like I said before, fields or properties and methods, right? Or the behaviors. So a class is kind of like a blueprint that enables an architect or developers, in this case, to build a three-dimensional object, three-dimensional house. And that house is what we call object at runtime. And that object has a whole bunch of properties and behaviors, or you can call it methods and fields or attributes that define the uniqueness, right? That object, what that object is. Now, I was talking about data encapsulations, right? The ability for the class or for the object to hide data inside the objects. This is OOP, Object-Oriented Programming Principle number 1, the ability to hide objects. Well, since we added, let me just go through this more advanced discussions here. That's principle number 1, data encapsulation. The second property is what we call inheritance, right? So it is very possible at runtime you have multiple objects sitting around, whereas object number 1 is the parent, right? Or the base class for object number 2. So what does that mean? Well, in family genealogy, right? You have the order hierarchies where you have grandparent, and then parent, right? And then what comes after parent? Children, right? So what happens is you have, let's just say, in a familial, right, trees, you have grandfather, right? And then underneath grandfather is your mom, right? And then underneath your mom is you. You see what I'm saying? So you have these inheritance structures. Same thing with OOP, right? Through inheritance, you have objects that are really offsprings of a parent class. And that parent class could be automobile or vehicle. And then a child class, right? Or object could be a more specific one, like Toyota, right? It is maybe not Toyota, I'm sorry. A vehicle is the parent class, and then what could be, let me just kind of draw this, right? So you can see it. This would have been a lot easier with it. So vehicle is V right here. And this is the inheritance structure. Inheritance structure uses this arrow. This is what we call UML, the Universal Markup Language here. Or sometimes people call it Unified Markup Language. But this allows programmers to kind of communicate what exactly you're talking about in OOP. So this is all used in the context of OOP, okay? You have V, which is the subclass, is the parent class. And then underneath it, you have car, okay? CAR, right? You can also have another a child right here. So what is another kind of type of a vehicle? You can have a boat, right? A boat is a vehicle, right? You can also have what? A bike, right? So bike is a vehicle too. B-I-K-E, I'm sorry, it's very hard to draw this thing. Okay, bike, car, and boat. So hopefully you get the idea, right? So you have a parent class and a subclass, and you can also have kind of branch out different types of cars. You can have different brands, Toyota, BMW, Tesla, right? These are all different brands, being the subclass, okay? Okay, so I'm not gonna keep on drawing this, but you get the idea. Classes can hide data. They can also inherit from each other. Inheritance is a very important thing because it reduces the clutter. It reduces the duplication in code. And reduction in duplication, reduction of code means that your program is a lot more efficient in the sense that it takes less time to load them in memory because the code footprint is not less. There's a lot less code in an inherited structure because you eliminate duplications right there. Because you can simply say A inherits from B, so I'm not going to rewrite the same logic that B has. A has it too, so I can eliminate that. So that is on a very high level what inheritance is. Code reduction and also the ability to make it more maintainable, right? Because now it's a lot clearer. There's no duplication in code, so the code is a lot leaner, so you can maintain it better. Okay, so there's a lot of benefit and pros and cons. More pros and cons in getting OOP in practices in contemporary programming. So I don't want to get too deep in it. So we mentioned data encapsulation, inheritance. There's also another benefit, another principle in OOP called polymorphism, the ability to change the size and shape of an object at runtime, given its characteristics. Now, understanding polymorphism, what that is totally beyond the scope of this class. Now, but if you're interested in pursuing other OOP languages like in a normal 16-week semester like C++, Java, you'll get to know more about these things, okay? So this is just a kind of a intro to what a class is. And taking a look at the very next one. Yeah, so this one is about class, and this one is about instance, right? So like I said before, the difference between class and instance, right? Sorry, I had to toggle back and forth. Class is your blueprint. So instance is your three-dimensional constructed house, right? So one can have an instance of a class, and this instance can have various different states. So the state is what we call properties, right? This is what we call properties. And the instance can have a whole bunch of methods, and these are what we call behaviors. And they must be happening at runtime, okay? So there is no instance if there's no runtime. So if you don't have a computer that can run this program with, there's no runtime, right? Runtime means that is dynamically created, dynamically allocated, and there is a CPU, a process that holds this entire runtime that allows you to run objects with it. Or when I say object, instance, okay? This object consists of a state and a behavior. So there we go. This is another example of the use of different things, but they're referencing the same as we speak, as we spoke earlier. The state being the properties and the behavior being the methods, right? Okay, so objects and instances are often used interchangeably. There you go. There you go. And make sure that you understand this. Okay. Okay. So there was class, there was an instance, and there's the methods. So these methods are part of the classes, right? So I just want to be super clear that in this case, we're not talking about functions here. So when we're talking about objects, we're talking about methods. So method is part of the class. It's part of, method is part of the instance, whereas function is completely standalone, okay? So method is part of the instance or part of the class, and that's very clear because if the method is all about bark and sit, eat things, and it's very possible that you have a pet class, right, or a dog class, and these things are what we call methods. So method and messages are used interchangeably. I think I went over this already, so just keep that in mind. Let's move on to the next one. You can do a directory on a given data type. So these are classes, right? So string is a class, float is a class, integer is a class, list is a class, and so on and so forth. So it's dictionary. And if you want to find out, this particular object's list of methods, you can do a directory on them, and this gives you. And so I went over this too. If you want to know what these methods are for and how they work, you can use. You just go to Python 3 documentations link that I did before. Or you can just do a Python 3. And whatever this type is, just Google search it and it will take you to the python.org, and that's usually the source of truth for all of the application programming interfaces out there. Okay, so try that one, and then you can see how each method works. So we'll take it from there. Any questions about Python objects? Okay. All right, here is a sample class. So let's just illustrate what this is. Okay, so now we're getting into kind of a nitty-gritty part. We talked about high level conceptually, from abstract container standpoint, what this object-oriented programming means, this paradigm means. Now we're talking about the actual implementation. So you would want to, to create a class, you use this thing called, you use this keyword called class. You can specify the name of the class. So by convention, we use what's called camel casing. So camel casing, so you guys know what camel is, right? It's an animal that runs in the desert. It's got humps in the back, right? So it goes up and down like this. So using a collection of upper lowercase characters, and typically by capitalizing the very first character of each word, and concatenating them together, meaning putting everything together, it creates some sort of camel, right? Camel humps. So this is what we call camel casing. You can also create class using snake casing. So in other words, if you use snake, so what does that mean? Underscore, okay? So you can have party underscore animal, right? Using a snake, concatenating them using snake symbols here. Although this snake casing is less, I don't see a lot of examples in the industry. People prefer this way. Usually people use camel casing to create, to create a name of the class. So this name of the class is called party animal. And of course, you're going to have a colon right here, and then do indentations here. And this is the very first properties that you get that you can, that you put x equals 0. So x is a property of party animal. So whatever this x is, usually you don't want to define something as abstract as A, B, C, or X, Y, and Z. Like I said before, it's a very bad practice. So spell out what that x is. Maybe the number of legs, or is a Boolean saying this party animal doesn't know how to fly, right? Is herbivore or carnivore, or is it amphibian, whatever that is, right? But don't use the x, okay? Anyway, so, and then you also have what's called a definition, okay? So this is very interesting. This is not a functions here, right? This is simply a def. So what is def? Well, def is a definition or is a behavior that is a part of that class. So this class has properties and those are behaviors. So what is def? Is a behavior, right? But we use definition or def keywords, right? Remember class and remember key and def, right? So definition, party, selves. What is self? Well, self is a itself, right? So imagine that you're creating this class or object out of a class at runtime. This object has a pointer pointing to itself. And typically in C++, we use, even in Java, we use this, THIS, not C++, not C, but C++. In Java, we use this, THIS, to refer to itself. But in Python, we use self. Self simply means itself. So what is self? Self is the object called party animal, okay? Now self what? Self.x. So remember though, every time you want to invoke or send a message to a object, you use the dot operator, right? So self.x means I want to refer to what's called this x operator. So this x property, right, is referred to as self.x in this fashion because inside this methods, how do you refer to itself? Or that self that contains this method, you have to use self pointer. So pointer is a data type in C++, but we use this interchangeably that points to the specific location of that object, which is party animal in this case. So the self is a pointer that stores the memory address of party animal instance. Okay, that's another way of saying it. So x is actually this x right here. Okay, so what is happening is that self.x equals self.x plus 1. What does that mean? Well, x is incremented by 1. So if you call party, right, this party animal, if you call party itself, this x is going to be 1, right? So this is not going to be 0 anymore, it's going to be 1, right? And then you can print so far self.x. So this so far dot, whatever this is, I'm sorry, so far, and print takes two variables here. So far, and then concatenating with self.x. So far 1, right? So and party animal. So let's talk about this too. This entirety of it is what we call the blueprints that we were talking about earlier. This blueprint allows you to spec out, right, specifications, the inner making of a party animal. Okay, how do you create a party animal? A party animal is instantiated. This is what we call instantiations, okay? This is dynamic creation of a party animal by assigning the dynamic create instance into this AN variable. So what is AN? AN is a party animal. It's a class. It's an instance of a party animal, in other words, okay? So party animal, open bracket, close bracket. So this is parentheses. It's what we call the constructors. This is default constructor on a party animal. So this constructor is, again, this is our first time talking about it. There's a lot of terminologies that I kind of throw around. But this is a construction phase. You're constructing an instance of a party animal by storing that instance or that address containing that party animal at runtime in memory space into AN as a variable. So this AN is an instance at runtime. You can invoke or send a message to its own method called party to essentially increment itself, this X by 1, right? So every time you do a AN.party, you're invoking this party methods. You're telling that object to, hey, can I invoke that party method, whichever, whatever the logic is inside a party, in this case, incrementing X by 1. So you're doing it 3 times, okay, manually. You're doing it 3 times. What you can also do, in this case, now remember that you don't specify it's kind of interesting, right? You don't specify self in it. Now this self is invisible. It is the same as creating, basically passing itself into it, okay? By convention, we eliminate the need to have to specify self at runtime. So basically, what is runtime? Runtime is, let me just close. Runtime is this. Okay, this portion is runtime, and this is static time. So let me just annotate this so you guys know. This is static. And what is runtime? Runtime is right here. Okay. So the runtime portion starts with this orange part, and it goes all the way down to the last of the pink. So at runtime, you're creating instance of a party animal, and then you're invoking party. And at runtime, you don't have to specify self because there is no self. Self is a terminology that we use in a static way, right? In a static way, in a static section of your code, self is being used to represent the memory address associated with the instance of a party animal. So at runtime, you can either pass, right, this AN into it, right? And that would point to this self basically, or you can eliminate it by default, okay? So by default, it is understood that you're passing an instance of it into it. So you don't have to do it at runtime. Okay, so this is how you, I'm sorry, this is not runtime. This is what we call instantiation at runtime. Instantiation at runtime, okay? Instantiation at runtime is the same as creation at runtime. You're creating this at runtime because this is only gonna be the case for you if you hit run. Otherwise, none of this runtime stuff is gonna happen, right? You have to hit yes. I wanna run it. Okay, so any kind of questions on this? Okay, all right, let's move on to the next one. So this is how you run it. Let's just assume that this party animal is all part of your party1.py, right? So let me just kind of run through a couple of the examples. So you guys know what this is. And just to remember though, every time you're dealing with Python, you have to indent it correctly, right? So there's 1 indentation here, and there are 2 indentations here, right? Because both self.x, right, and print, both of these are part of the def party or these methods. So you gotta make sure you have the right indentations. And then as soon as you exit, so there's actually invincible boundaries between these 2 parts. So part 1 is the static portion, and part 2 is your runtime portion. So at runtime, what's going to happen is Python party1.py does 2 things. One is it compiles this Python file and then runs. So compile and run both happening at the same time with this statement here. And this statement leads to the creation of animal called AN and the invocation of party, which is this thing that increments X and then prints something on the screen 3 times. Okay, instantiation and then invocation 3 times. Okay, a specific method 3 times. Let's clear this and move on to the next page. So what's going to happen is when you run this very first time, you're creating an instance of AN, and AN has a X equals 0 and party methods, right? So this yellow one is the property, and this green one is the method associated with it or the behaviors. So when AN is just created for the very first time, by default, X equals 0, and there is a party method in it and nothing else, right? So that is what is the orange part is, right? Whichever line this is. So what I want to do is to invoke party on AN 3 times, 3 in a row. So this is what happens. So very first time that it invokes it, what you get so far 1y. Well, because X has already been implemented, right? And this is exactly what happens. When you call party, it's by default passing what's called an implicit AN in there, right? So if you scroll to this part, you'll see what I meant, right? So there's actually a AN that gets passed in here, party animal dot party AN. So these are equivalent. What's the equivalent? Whatever's on the left hand side and the right hand side. Both of these are the same, okay? But because writing the right hand side part is much more cumbersome than writing the left hand side, we prefer to use the right hand side, okay? Left hand side. So this is what happens when this is called 3 times. Your party is going to call 3 times, which means that your self.x equals self.x plus 1 is going to be called 3 times. So the first time self.x is 1, and when you print it so far self.x, right, you're getting 1. There should be actually there should be a space here. Okay, there's so far and then far and the double quote. There should be a space in between. This allows you to inject that space right here. Okay, that said, the very first time dot party is called, you get 1, and then second time it gets 2, and then third time it gets 3, right? So this is what happens. And self is a pointer pointing to itself. Even though there is no self here, it's implicit passed. It's implicitly passed into the party when it is invoked. Okay, does it make sense? Any questions about this? All right, let's move on to the next one. Okay, this one is playing with directory and type. So like I said before, you can key in the directory command to see a list of properties and methods. So by default, all of the properties starts with the underscore. So there's an underscore. There's 2 underscores at underscore. Actually, these properties are typically hidden. So these are hidden or what I called sort of native to this list. You can still invoke it at some point. You may want to compare whether this particular instance is of the same class as the other one, right? So you can still invoke, even though it's used by Python itself, you can still kind of invoke it. So that is kind of knowing what this API is and then make use of it. But most of the time, you will stick with what is in green here, which are the real operations, and these are typically public, meaning once you have the instance, you can dot methods, meaning those methods are public, so you can make use of it. Or you can make a type, basically call a function type on that instance, which tells you which class that instance belongs to. So if you do a type y here, you'll see that this is our class list. Then you know y is a list, right? At runtime, it's a list object. A list object having these methods at runtime, okay? And these properties. So properties and behaviors, right? Could be found through use of type and then the directory on that, okay? All right. Okay, so this is another kind of use case. We went through completely whatever's in white in the last 2 slides. We can use directory find the capabilities of our newly created class. So this is exactly what I'm doing. I'm doing a type on an AN now, and then type on an AN, so a directory on it. So if you do a type, and you can see that this is main party animals, what does that mean? Well, this tells me one thing. One is when you are, so main generally means console applications. So you're running a console application which outputs in a console. console is your terminals in console, or CMD in Windows. It is main dot. So this is of the main class, and inside the main class there's a party animal class. So this is a nested class sitting inside of the main. So main is your operating unit, kind of runs Python, and party animal. So it's basically saying that your type AN is of party animal class. Okay, because this says class right here. And this particular party animal class happens to be a part of your Python main, right? Okay, so that said, you can also do a directory AN, and you can see that it has actually several attributes that are part of your native Python, so you don't have to worry about that. But it also has a party, and also a method called party, and a property called X. Okay, so both method and the properties are displayed as part of the directories on AN. Okay, so yes, you can use type and directory to find out a lot about this particular class. Okay, so any questions about this? All right, cool. Let's move on to the next one. See, I don't know how much you want to just keep going on this, but I think there may be a use case. I don't know how to, I don't know if I want to run the class, but this is simple enough. You can run this also in your IDE there. But I need to context switch. So let me just kind of keep going on this. Okay, so the very next slide shows a directory with a string. You can do the same thing before, like we did before. X is a string, so if you do a directory on this X, you're gonna see a whole bunch of methods associated with this string, and its properties and behaviors, right? Okay, object life cycle. So this actually goes into what we call constructors that we did earlier, that we mentioned earlier. Constructor is your entry point to creating this object. So every time when you're, let's say at runtime, the very first time that you see an object created, that creation is through constructors, okay? And then, so this is a life cycle. The objects are created the moment that you did, for example, list L equals list parentheses, right? Something like this, right? This creates an instance of the list. That instance of the list is called is L, right? So this is how objects are created, kind of like now, basically objects are created through what? Through this constructions, right? Once L is created, then is used, right? So you use L to do what? To store data, right? And then what happens is after you're done, as in your entire program is basically done, and it's about to exit, then what's going to happen is this L, right, is then discarded, right? This is what we mean by object life cycles, right? So if you think about this, if you look at this entire object chain, the construction happens here, right, at the very beginning, right? And then it's going to be used somewhere from here to here, okay? At some point, it's probably not going to be used, but it's going to be used again. Sometimes it doesn't get used, and then, right? But towards the end, the discard happens when the program exits. And that's how the entire object life cycle is kind of delineated from the beginning of its life to the end of its life, right? And the moment of creation is called constructor. The moment of destruction, meaning the end of its object life cycle, is what we call destructor. So we use constructors a lot. Okay, so we did that already with lists, right? Every time you have the parentheses with nothing inside. Sometimes you have something inside too as an argument. Fine, either way, we're calling these things constructors. So constructor name is the same as your class name. So party animal. So party animal parentheses, closing parentheses is a party animal constructor, which is public. So we use that a lot to create instances, right? But we don't use destructors a lot. So destructor carries specific purposes, meaning before the program is about to end, I want to make sure that all of the memories and stuff, they get deallocated, meaning they're reclaimed back into the memory pool. I don't have to worry about it. Now, you will go through what's called destructors for that kind of stuff. We don't call destructor, and destructors are not used a lot for a good reason. A lot of times when you exit the code, your program ends. That basically means all the objects are liberated, right? Not liberated, but obliterated, meaning they're deleted. So why do you have to call destructor? What's the point of doing that if you know by shutting down your program, everything would have been gone anyway? Therefore, destructors do not get used a lot, but it is there, right? So if you look at C, C++, you'll see, actually not C, but C++ in Java too. Actually, no, not even Java. Java has a garbage collector, but in C++, you can rely on destructor to delete dynamically allocated memory spaces. And because pointers used quite a bit in C++, destructors are often used to delete pointers that points to an array or something like that. But in Python, it's rarely used. Okay, so I just basically let you know, first of all, what constructors and destructors are, and the reason why they're used, and how they're used. Okay. Any questions about this one? All right, so the primary purpose of the constructor is set up some instance variables have the proper initial values when the object is created. Sure, what does that mean? Okay, so this is kind of a very basic anatomy of a class in Python. So this shows a whole bunch of stuff. First of all, what is the name of the class? Party animal, right? And colon. And then you see the indentations here, right? This indentation is very important because it allows your Python to compile this into code, into a executable. Now, this party animal also has three classes, methods. So the first one is called init, second one is called parties, the third one is called delete, right? So let's take a look at the very first one. So constructor. In C, not C, but C++ and Java, constructor name is the name of the party animal, the name of the class. But in Python, they use underscore init, okay? Underscore. So this is an internal, okay? This is the internal methods. So sometimes people said a constructor is not a method. Some people do say that it is a method. So you can think of it as an internal method, which is constructor for party animal, okay? And the reason why I say constructor for party animal is because this constructor actually lives inside party animal. So it is actually party animals constructors. And party animals constructors, or any constructors, take itself as a invisible pointer to it. So this self doesn't really do anything because all you do in this constructor is you're printing I am constructor, right? So it is, if you call this a party4.py, when you do a Python and compilations and running, the very first thing that you get is I am constructor, because constructor is the entry point for all of the construction of the objects. So you're getting that one printed first. Okay, so the second method is called party. This party also takes self. And of course, we know that self increments itself. And delete, right? Underscore delete. This is what we call destructors. This destructors doesn't really use quite a bit. And if you don't have it, Python will supply one to you. But if you do have it and have something in it, then effectively what happens is you're overriding the default behavior, which is nothing, with a print I am destructor, blah, 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 self x. So this allows you to print self.x. So what is self? Self is itself. So what is this x? X is, of course, itself, right? Like right here. Okay? So far one, so far two, right? The reason why that is the case is because I'm printing this twice, right? One time, second time. And then the third one is I'm destructor. What does that mean? Well, AN 42, right? And then it says AN contains, where this is 42. But the question is, how come this IM destructor 2 is called? Well, the reason why this destructor 2 is called is because AN is reassigned. Okay, so this is what happens at runtime. There is a memory space, and this one memory space is called, it's AN. Okay, so AN is kind of like a label pointing to this location. This location, memory location, is pretty big, and it has a whole bunch of stuff in it, namely party animal. Now, when you say AN equals 42, what does that mean? That means you're reassigning AN, right? Which means this entire block that we have right here is all gone. So gone is not good. Gone means that it is forever lost. So you lose that space there. So what happens is Python actually automatically collects or reclaim that one by deallocating it. So this delete, right, or destructor is basically called the moment that AN is reassigned to 42, okay? And that triggers a destruction or destructor being called. And of course, inside the destructor, it prints the self X at that point, which is 2, okay? So this allows you to first construct it and then kind of figure it out, you know, in transit, in flight, what every single one of these lines is. And then you have IN destructor 2 right here as a kind of a bonus point when AN is certainly assigned to something else. And of course, the entire program hasn't completed yet, right? The very last line of that program is AN contains 42, right? So this explains the entire life cycle from beginning to end. Does it make sense? Does it make sense to you guys? Okay, so let me just kind of erase this. So in object-oriented programming, or OP, a constructor in a class is a special block of statement call when an object is created. Okay, again, you should go to this Wikipedia. This will give you a lot of examples of what I just talked about. Okay. All right, cool. Yeah, so I don't know if I wanted to keep going. I think there's a lot of the ideas that are here that might be, you know, kind of, you know, at this point, this is definitely a lot of stuff I'm introducing. You can also see, you know, at some point you have a party animal constructor that takes 2, you know, parameters that goes in there. One of them is itself, which is always by default the case. This constructor actually has one user-defined variable, and whatever that z is, you're assigning z to the name itself. So you can, I don't know, I'm hoping that maybe you can see what's going on here, right? The fact that you're calling, you know, S as a party animal Sally, and this S is really Sally at runtime. So Sally becomes Z, and Z becomes the name itself. So this allows you to create a party animal with a label called Sally, and its name is changed to Sally. And this one allows you to create a party animal Jim, right? So you have S Sally dot party and then Jim dot party. What does that mean? Well, this dot party increments itself and also prints itself name-wise plus, right, the X that gets implemented. One thing about X is this one is being used per instance of party animal. So S, which is Sally, right, is different than J because they occupy different memory spaces. And this allows you to kind of separate different objects and calling each object in a different realm without collecting, without collisions. So, you know, going back to what we were talking about constructors, many instances, you can create a lot of these things, and every single one of these objects is distinct from each other, meaning there is an invisible boundary between the two because they're occupying 2 different spaces, different memory spaces. They do not share the same functionalities. They do not talk to each other. There is no way one object talks to the other unless you specifically tell it to do so. But you're not in this case, okay? You're simply just creating instances of it. Like I said, S, J, and then you invoking each other's through its own, each other's internal methods. So so this is how we, kind of, run the code by having a static definition of a class called animal, and then the runtime definition and declarations of running the specific instances of the party animal based on this template. So that said, it is very important, right, to know that at runtime, you have to let your Python code to what a class party animal is. So in other words, this top portion, right, that I just circled, is loaded already in the memory, right? So this allows you to print, basically make copies of this, right? And then invoking their methods accordingly, or messages accordingly, okay? So this is not like JavaScript where you can have class defined, be after the invocations here, because in JavaScript you can hoist at runtime, meaning your runtime environment is going to check to see the existence of a party animal. If not found, it will go straight down first, hoisting them up. It takes a little bit of pre-processing, but in Python, it doesn't work that way. So make sure that your class is kind of defined up there, and then the usage portion is underneath it. Because Python actually, what it does for, just like any other programming languages, at runtime, interprets lines of code one line at a time, starting with line 0. Okay, so by the time you're done, with the class party animal, this entire class would have been stored in memory, allowed for it to be invoked or created or instantiated. So party animals, party gems will not give you exceptions, because class party animal would have been loaded in memory, okay, at that moment in time when this S and J are called. Any questions about this? Okay, let's see, what else? Yeah, this is exactly the same thing as before, and I think we're running the same codes as you can see here. Okay, so this is kind of like a fast forward version of what I had earlier. You have S and J, and S and J are both in two different language memory locations. So X could be X times FA1, J could be in 0 times FZ23, right? Two different memory locations referenced by these two green boxes. So two independent instances here. This is all fine and dandy. Let's print it. So Sully constructed, Jim constructed, Sully party count 1, party count 2. What's going on here? Okay, so to understand it, let's just make sure that we understand where this point of contact is. So this one prints Sully constructor, because party animal, when this one is invoked, it's calling this guy right here, okay? This is our constructor that goes into this code base right here, and sniffs the party name. So this party name, Z, is Sully for this guy. So you'll see S now has been instantiated with a name, internal name called Sully, right? And it prints this out. So that's why you see the very first line. So Jim is the same thing. Jim gives you the constructor, right? Calls the constructor by initializing self name to Jim, and it prints it, okay? And s.party is Sully party count 1, because this gives you the what is it? Self.party actually prints this guy, prints count and self.x. So this gives you 1, because self.x is 1. See, at some point, s.party gets called again, and then you have this party 2, party 1, right? So it increments it. But J is completely separate from J, from S. So J has his own X, so to speak, in there. Does it make sense?